Differential equations. Definitions. Here is some terminology I will be using throughout this lesson. Differential equation. A differential equation is just an equation that involves derivatives. Initial condition. A condition or set of conditions on the solution to a differential equation that will allow us to find a particular solution. A differential equation with an initial condition is called an initial value problem. And a set of conditions will be used depending on which derivative is given, and we'll see an example of that towards the end of the lesson. General solution. The general solution to a differential equation is the most general form of the solution and doesn't take into account initial conditions. The graph of the general solution forms a family of solutions. And finally, a solution. The solution to a differential equation is the specific solution that not only satisfies the differential equation, but also satisfies the given initial conditions. Let's go ahead and take a look at an example. Solve dy dx equals 3x squared given y of 0 equals 2. This is an example of a differential equation because it's an equation, there's the equal sign, that involves a derivative. So the derivative notation we're looking at is dy dx, and then on the right side we have a function 3x squared. So let's take a minute to remind ourselves of just an equation that we should be familiar with solving. Let's go ahead and say something like 3 plus x equals 5. So we would recognize this as an equation. There's the equal sign. And there's something very clear that stands out to us is what we're solving for. We're solving for what's missing. We're solving for x. And just simply by looking at it, and because we've solved so many equations of this form, we know that the solution is that the x value that satisfies this equation is x equals 2. So here, notice we have something missing that's represented by a variable, and we have an operation of addition that we would be undoing when we solve this algebraically by subtracting 3 from both sides. So when we subtract 3 from both sides, we're doing the opposite operation of addition, which is subtraction, to get that x variable by itself and solved for to the numerical answer of 2. So this is after many, many years of solving algebra problems that we recognize that x is the variable that we're solving for. So now keep that in mind as we look at the differential equation. Just looking at the differential equation, dy dx equals 3x squared, you might be thinking, what exactly am I solving for? So what I'm going to go ahead and do is rewrite this. So dy dx can be rewritten as d dx of the variable y, so the derivative of y equals 3x squared. So now, the variable that I'm solving for is actually going to be y. So your inclination might have been to solve for x because of the way we're used to solving equations, but a differential equation means we're actually solving for a function. So what function did I have to take the derivative of to get out 3x squared? So we have something we're solving for, y, and we have this operator, d dx. Just like addition was the operator in the initial equation that we could solve algebraically. So in order to undo a derivative, we should be thinking by now integration. So if we integrate both sides, we're going to be able to get this y here independent and its own function. Now this part over here, y of 0 equals 2, is our initial condition, but we'll handle that in just a minute. So I'm going to erase this because we don't rewrite differential equations of this form. That was just to get you to understand that y is the function that I'm solving for in the differential equation. So let's go ahead and erase that. Here's how we do solve differential equations. The first step is we're going to want to get all the variables on their own separate sides. So I want to gather all terms with an x in it on one side. So I'm going to go ahead and multiply both sides by dx. So on this left side, the differential dx is going to cancel, and I'll end up with dy equals 3x squared dx. And now at this point, remember I said we were going to try to get rid of the derivative, and to do that we were going to take the integral. So integration of both sides will allow us to solve for our y. So on the left here, we really have the integral of dy, and there's really a 1 here. So the antiderivative of dy is going to be just y. And you might be thinking, why aren't you writing plus c? Because if I have a general antiderivative, I need to put a generic constant, but I'm only going to put a plus c on the right side, on the side with the variable x, or really on the side with the independent variable. So let's go ahead and take the antiderivative of the right side. So here we're going to add a power, divide by the power. So we're going to have x cubed. And if I divide it by 3, that's all that's going to be left. And like I said, I'm going to put the generic constant on the right side. So really, the antiderivative on the left would yield a constant, but we can just add that constant to the other side and turn it into just one generic constant. And again, I'm only going to leave it on the side with the independent variable x. So y here depends on the variable x, so that's why x is the independent variable. So what I've done here is I found what's called the general solution. So this plus c, if I could figure out what plus c is, then it would be a specific solution. And that's where this initial condition comes in. So if there were no initial condition, I would be done. Y equals x cubed plus c is a solution, a general solution, to this differential equation. But I do have an initial condition, and here's where it comes into play. It's going to allow me to find this constant c to be a specific number. So here, y of 0 equals 2 means that I'm going to let x be 0, and that must mean that the output value of y has to be 2. So I'm going to solve that on the side as its own separate problem. So when I plug in 0 for this x, I'm going to get 0 cubed plus c equals the output value 2. So 2 is my value of c. And now I'm going to go ahead and substitute 2 back in. So y equals x cubed plus 2 is my solution to this differential equation with an initial condition. Since it has an initial condition, it can also be referred to as an initial value problem. So y equals x cubed plus 2 is the solution to my differential equation. Alright, so steps for solving a differential equation. We just walked through them, but to have them written out explicitly for you, the first thing we're going to want to do is gather the same variables on opposite sides of the equal sign. Then integrate both sides with respect to their appropriate variable. Next, even though both indefinite integrals will yield the generic constant, by convention we're only going to include that plus c on the side of the independent variable. And in most cases, the variable is going to be x or t that we include the plus c on. Next, if provided, we use the initial condition to solve for c as a number. And then the last step is going to be to substitute the value of c back in and solve explicitly for the dependent variable. And that dependent variable is usually going to be y. So now let's go ahead and try a different example. Alright, let's work through another example. So solve dy dx equals 4x to the 7th given the initial condition y of 0 equals 4. So here we're going to go ahead and start by multiplying both sides by the dx. So we get dy equals 4x to the 7th dx. And then we're going to integrate both sides. So the integral of dy and the integral of 4x to the 7th dx. On the left side, just like last time, we're going to have just the y variable. And on the right side, so if I add a power, I'm going to get x to the 8th. And then I'm going to divide by 8, so I have this 4 on the outside. So 4 divided by 8 is going to give me a constant of 1/2 in the front, plus my generic constant c. So since I have an initial condition, I'm going to move that problem off to the side to solve for the constant. So when I plug in an x value of 0, I'm going to get out a y value of 4. So looking at this equation, 4 is going to have to equal 1/2 times 0 to the 8th plus c. So c must equal 4. So now the last step is to write the specific solution, 1/2 x to the 8th plus 4. So that one's pretty similar to the last one, and it won't always be the case that the x value that we substitute in is 0, making our constant always 4. We're going to see an example next where we have a different form of an initial condition. Alright, an example that now has a few things different. For one, I have solve y prime equals sine pi t given y of 2 equals 2. So we have a few things that have changed here. The first is that we no longer have the dy dx notation, we have the y prime notation. But it's the exact same type of problem. We're still trying to find that y, that initial function that I wanted to take the derivative of to get out sine pi t. And then the second thing that's different is that our initial condition is no longer substituting in 0, we substitute in 2. So if we want, we can go ahead and rewrite it as dy dt. So the independent variable has changed to a t. So dy dt equals sine pi t. So that now we can multiply both sides by dt and arrive at dy equals sine pi t dt. And now we can integrate both sides. So the integral of dy equals the integral of sine pi t dt. Alright, the left side is just y. And the right side, we need to take the antiderivative of sine pi t. So because of the pi on the inside, we're going to end up with 1 over pi in the front. And the antiderivative of sine is going to end up being negative cosine. So we're going to have a negative 1 over pi cosine pi t plus c. So now, at this step, we have an initial condition, so we're going to want to substitute the initial condition into our general solution to solve for c. So we're going to get out a value of 2, so 2 is going to equal negative 1 over pi cosine. If I plug in for t, 2 cosine of 2 pi plus c. So cosine 2 pi is the same as cosine 0, and cosine 0 is 1. So what I have is 2 equals negative 1 over pi times 1 plus c. So now, solving for c, I'm going to add 1 over pi to the other side, so 2 plus 1 over pi equals c. And then I'll substitute this value of c back into the general solution to get a specific solution. So y equals negative 1 over pi cosine pi t plus 2 plus 1 over pi. So that's definitely a different constant that we solve for, but it is a constant. 2 plus 1 over pi is just a number. And it was different in the fact that we didn't just plug in 0 for the t value. Now we plugged in a number and we got out a different type of constant, but still only a number. So this is my specific solution to the initial value problem given. Alright, let's take a look at the next example. Solve y prime equals 10e to the negative 2x. So notice this problem does not have an initial condition, but that's okay because we're just going to leave our answer as a general solution. So here we have the y prime notation again, but we don't have to rewrite it as dy dx. Let's just go ahead and start by saying that our solution, y, is going to equal the antiderivative of 10e to the negative 2x dx. So that's what we would have arrived at on the left if we have rewritten it as dy dx, moved the dx to the other side, and taken the antiderivative of dy, we would just end up with the y. So we can go ahead and skip that part and jump straight to the y that we're solving for. So this antiderivative on the right, y is going to equal, well, e to the negative 2x will stay e to the negative 2x but we will end up with a negative 1 over 2 from this negative 2 up here. So negative 1/2 times this constant 10 will give us negative 5 in front of e to the negative 2x. So negative 5 e to the negative 2x plus our generic constant c is the solution to our differential equation. So since there's no initial condition, we just stop at this point and say that this is the general solution. Alright, taking a look at a different example, solve y double prime equals 3x plus 2 given y prime of 0 equals 1. Alright, so this is different than what we've done previously because now it involves the second derivative. But if you recall the definition of a differential equation, it's an equation that involves a derivative. So here we have a higher order derivative, but that's fine because our initial condition involves the derivative that came right before it. So here, solve when the second derivative is 3x plus 2. What they're asking for is, well, what came before that? So they're asking us to find y prime. So in the previous example, they gave us the first derivative and asked us to find the original function. So this time they're giving us the second derivative. They're asking us to find the first derivative. So here we're using the prime notation again, but we can jump straight to saying that we're looking for y prime. And y prime is going to be the antiderivative of 3x plus 2 with respect to x. So let's find the antiderivative here. So we're going to get 3x squared over 2 plus, here we're going to end up with 2x plus our constant c, and that equals y prime, the first derivative. But here we have an initial condition and one that works out for us because it's in terms of the first derivative y prime. So whenever we plug in 0 for x in the y prime function, we should get out a value of 1. So working off to the side here, we have that 1 has to equal, so if I plug in a 0 here, I'm going to have 3 over 2 times 0 squared plus 2 times 0 plus c. So everything except the c on the right side goes away, so c equals 1. So that must mean y prime equals 3 over 2x squared plus 2x plus 1 is our specific solution to this differential equation. So nothing changed here except that instead of being given the first derivative and an initial condition regarding just the function y, now we're given the second derivative and we're given information about the first derivative. But almost exactly the same setup, and our answer is a first derivative with a specific initial condition being used. Alright, so before we move on to an application problem, I want to go back to the first example and talk strategy for a second. So by the time we get to the AP exam, and by the time you get to a test, there are a lot of different types of problems that you've been exposed to. And a key part about the exam is going to be being able to recognize the different types of problems. So here, to recognize that this is a differential equation, it's different than seeing just the operator d dx in front of a function. So here we have dy dx, a derivative, equals 3x squared. And a really big indicator, although it won't always be there, is this initial condition, so that you think initial value problem or that you think differential equation. But something that I don't want you to get this mistaken with is just a regular derivative. So thinking that the answer to this might be 6x and just using the power rule. So in other words, this is not the same as d dx of 3x squared. So when the operator d dx, take the derivative of 3x squared, is right in front of a function, then the answer to that would be 6x. But this sentence, I want you to be able to read it as the derivative equals 3x squared. What was the original function that I had to take the derivative of to get to 3x squared? And more specifically, what was that function if, when I plug in an x value of 0, I get out a y value of 2? So this problem here and this problem are two completely different problems. And another quick thing I want to mention is we can never ever ever split up this operator. So just like we can't split up a plus sign, right? This plus sign wouldn't make any sense to just write a line. So we can't split up a plus sign, that's an operator, so I cannot split up a d dx. So I could not ever just multiply both sides by dx in this case at all. Something like that would never ever work. And that's different than what we did over here. So dy dx is a derivative. Remember, it's like a noun. As opposed to d dx is an operator. It's telling me to do something, take an action. So it cannot be split up. So that's not something that I can do. So I really want you to be able to recognize the difference in the types of problems. So now let's go ahead and move on to an application. Alright, an application. At time t equals 0, a car traveling with velocity 96 feet per second begins to slow down with constant deceleration, a equals negative 12 feet per second squared. Find the velocity v of t at time t and the distance traveled before the car comes to a halt. Alright, so let's go through the problem and trying to write down the information using mathematical notation. At time t equals 0, a car traveling with velocity 96 feet per second. So at time t equals 0, the velocity of the car is 96 feet per second. So when I substitute the time 0 into the velocity function, I get out 96 feet per second. Now, at that time, the car begins to slow down with constant deceleration, a equals negative 12 feet per second squared. So this word here, constant deceleration, means that no matter what, the acceleration of the car is going to be negative 12 feet per second squared. So I've also been given that a of t is negative 12 feet per second squared. Find the velocity v of t at time t and the distance traveled before the car comes to a halt. So there's two different problems here. Find the velocity v of t at time t. So let's stop right there. Find the velocity at time t. So here's my acceleration function, negative 12 feet per second squared. And then here, this should strike you as an initial condition. So it's information about the velocity function, which is going to be the antiderivative of acceleration. So here I have a of t, which is really v prime of t. So v prime of t is negative 12. So that must mean if I want to get to velocity, I have to take the antiderivative. So v is going to be the antiderivative of negative 12 dt. So I'm using the variable t since our independent variable here is time. So if I take the antiderivative, v is going to be negative 12t plus c. So I have this generic constant here, but I don't need to have it because I have an initial condition. So my initial condition tells me that when time is 0, the velocity is 96. So I can go ahead and solve for c because the velocity is 96 when I plug 0 in for t. So c must be 96. So the velocity function at any time t is given by the function negative 12t plus 96. So find the velocity v of t at any time t. So here's my velocity function. V of t equals negative 12t plus 96. So I can plug any time into here and get out a velocity. So I've answered the first part of the question. Now the second part of the question is a little bit more intense. So find the distance traveled before the car comes to a halt. So when I see this word distance here, I need to be thinking about the position function. So the location of the car tells me about how far it's traveled. Right now, all I have is this velocity function. So what I need to do is I need to find the position function. But remember, the relationship between position and velocity. The first derivative of position gets me to velocity, so that must mean I need to take the antiderivative one more time to find my position function. So over here, we're solving for, so let's just go ahead and write this as s prime of t, we just found, is negative 12t plus 96. So what I'm interested in is s. So s is the antiderivative of negative 12t plus 96 dt. So now I can take the antiderivative. So negative 12t will become negative 6t squared plus 96t plus c. And this is my position function, except I don't want a plus c in there. So now the question becomes, do I have an initial condition regarding my original position function s? So do I know anything about the position function s? Well, at time 0, I want to be able to determine the distance traveled before the car comes to a stop. If I started recording at time 0, then the car hasn't gone anywhere. So that means s of 0 equals 0. So I do have an initial condition, but it requires me to think a little bit. At time 0, the car hasn't traveled anywhere. That's when I'm barely starting to record information. So I haven't recorded any information about a distance traveled. So s of 0 equals 0. So now I can finish solving for this constant c. So when I plug in 0, I get out 0. So 0 equals negative 6 times 0 squared plus 96 times 0 plus c. So c equals 0. That works out nicely. So my s of t function is negative 6t squared plus 96t. So here's my position function, but I haven't answered the question. So I need to know how far the car has traveled, the distance traveled before the car comes to a halt. So we're going to need some more space for this problem. Alright, so we have the equation that we need. We have this equation regarding the position function. So an object comes to a stop when its velocity is 0. So what I'm going to need to do is figure out when the velocity function is 0, because that's when the object has stopped, and then figure out the difference in the position of the object from when it started versus when it stopped. So using the velocity function to figure out when the object come to a halt or stopped, I'm going to set v of t equals negative 12t plus 96 equal to 0. So negative 12t equals negative 96, or t equals, divide by negative 12, I'm going to get positive 8. So at time t equals 8, the car has stopped. So what I need to do is figure out the difference in the position from when the car started versus when the car stopped. So the equation I'm going to set up is s of 8, so the position when the car stopped, minus the position of where the car was at when it started recording at time 0. And since this is a distance we're talking about, I want the distance to be positive. So I'm going to need to plug in 8 and plug in 0 into my position function to solve for the total distance traveled. So if we do that algebraically, the answer we get out is going to be negative 6 times 8 squared plus 96 times 8 minus, if I plug in 0 for each of these t's, I'll get out 0. So it's going to be this number in absolute value bars, which is a lot of algebra, and it turns out to be 384 feet. So I want to make sure my answer makes sense. My answer is a distance that's plausible. 384 feet is the total distance traveled after 8 seconds has passed.